Welcome to the Flight Readiness Review of Phoenix 3, the 2019 UAS for the Unmanned Aerial Vehicle Team at the University of Texas at Austin. Phoenix 3 is the third generation of UAV Austin's Phoenix aircraft program, featuring fully custom hardware with enhanced software systems. So without further ado, let's meet the team. Sean Lee, Team Captain and Program Manager. Pranav Sridhar, Flight Hardware Lead and Internal Systems Lead. Rhythm Sharma, Mission Strategist and Ground Station Lead. London Darce, Mission Planner Pilot and Ground Station Team Member. Bradley Bridges, Flight Software Lead and Chief Software Engineer. Anthony Chang, General Software Crew and Infrastructure Team Member. Bennett Ramirez, Software Troubleshoot Crew and Infrastructure Team Lead. Paige Williams, Image Recognition Lead. Haoyang Yu, Manual Image Recognition Crew and Image Recognition Team Member. Phoenix 3 is a custom-designed, fully composite aircraft that was developed around the parameters set by the 2019 AUVSI SUAS competition guidelines and the derived requirements of the team. Phoenix 3 was designed primarily around the Unmanned Ground Vehicle or UGV payload and a nose-mounted camera gimbal. To avoid a traditional twin-boom pusher configuration, Phoenix 3 features a unique boom prop configuration where the propeller is coaxial to the tail boom. Phoenix 3 features detachable foam core fiberglass wings with Kevlar hinges and unidirectional carbon fiber spars, a conventional tail configuration with a carbon fiber boom, and custom rear landing gear made with unidirectional Kevlar. Phoenix 3's onboard systems feature a 3D printed camera gimbal with a 360-degree 2-axis rotation and a vehicle bay which houses the 3D printed UGV that uses a deployable parachute system for descent. Phoenix 3 runs on a triple redundant power supply to support fail-safe flight in the event of critical failure. The microcomputer, PICSOC 2.1, handles mission-critical tasks such as basic telemetry, actuation, automated flight, and communications. More advanced aircraft features, such as image recognition, waypoint selection, and obstacle avoidance, are executed through an onboard NVIDIA Jetson TX2. Two 2200 mAh LiPo batteries power the microcomputers, radios, and servo rail, while two parallel 6000 mAh LiPo batteries power the propulsion system, providing a nominal flight endurance of 45 minutes. At UAV Austin, we strive to develop the most reliable software. With that in mind, the team chose to design a contained microservice architecture that is easy to test and deploy. To allow the sub-team to move rapidly, we employ Scrum techniques, such as stories, sprints, and stand-up meetings to ensure that all members are on the same page and are achieving results in every meeting. This year, UAV Austin has made headway in all software sub-teams. Autopilot, which has designed a novel algorithm for obstacle avoidance, Image Recognition, which has developed and trained a brand new neural network with a 0% false positive rate, and Infrastructure, which has been constructing a logging system to make the whole system as transparent as possible to the flight operator. The team prioritized ease of development and the use of the software system on the flight line to reduce the amount of time spent in configuration and debugging the setup. A portable server rack was configured with a server, router, networking switch, and power strip all configured together to prevent needing to set up ground station networking hardware on each flight. This reduces error and labor in setting up both the hardware and setting up the software to run on the flight line. Testing was prioritized in development to minimize errors in code on the flight line. This was possible through the use of writing unit and integration tests where appropriate. Critical parts of the software stack, those relating to telemetry and interoperability system communication, were tested closely alongside instances of the interoperability system and a simulated plane and integration tests. Continuous integration was configured to enable the tests to run on each code commit to prevent regressions entering the mainframe of the code repositories. UAV Austin is confident in executing all 2019 AUVSI SUAS mission objectives with Phoenix 3. Phoenix 3 plans to successfully conduct autonomous waypoint navigation, obstacle avoidance, unmanned ground vehicle delivery, object detection, classification, and localization. The expected performance of the unmanned aerial system was based on task-specific tests as well as full mission tests. Here are the confidence levels of success for each task. Developmental testing is an integral part of UAV Austin's design, manufacturing, and operational processes, ensuring the consistency of the team's systems and the safety of the members. For hardware systems, component tests were conducted in real and virtual simulated environments with controlled variables in order to verify their functionality. The 2018 competition UAS Surveillance 2.0 was utilized as a testbed vehicle during hardware developmental phases. All software systems were tested using the software-in-the-loop testing method to make sure its compatibility with the UAS hardware after being verified with numerous unit tests. In addition, simulated ground tests as well as virtual flights using a flight simulator were conducted before each test flight of Phoenix 3 to ensure operational excellence and mitigate possible system failures. Phoenix 3, being a new aircraft, needed important flight controller parameters tuned to ensure that the Pixhawk can safely and efficiently fly the aircraft. The aircraft tuning sequence was accomplished in two major parts, PID and TECS. The PID stability parameters were tuned via rapid rolls and banks to calibrate the speed and accuracy of the control surface's response to those inputs. On the other hand, the TECS parameters were tuned in both manual and autonomous modes to ensure that the flight controller properly could balance the trade between altitude and speed. The entire process took approximately 90 minutes to ensure consistency and accuracy of the flight controller during different flight conditions and scenarios. The aircraft had been flown by our safety pilot in weather conditions ranging from clear windless skies to cloudy, windy conditions. Being able to fly and tune in these conditions helped to diversify the controller's ability to safely fly the aircraft. Flying different flight paths autonomously, Phoenix 3 has spent about 100 minutes flying without the need for manual takeover from the safety pilot, and more minutes will be added up to the time of competition. The variation in waypoint configurations has allowed the ground station team and flight controller pilot to observe the aircraft's navigational capabilities and waypoint accuracy. For the 2018-2019 season, the team devised a new algorithm that maps the field onto a graph upon which the pathfinding algorithm, Tangent Assisted Navigation, or TANSTAR, can be run. The new algorithm offers improved performance over the old one by eliminating the necessity to discretize the map, but finding critical points in the continuous space and using those to construct a graph. Furthermore, the algorithm natively takes into consideration the plane's bearing to generate optimal paths. During the testing stage, the team wrote 28 unit tests to ensure modular correctness and 8 integration tests to test overall system performance. Over all integration tests, the algorithm in total generated over 5,600 vertices. On average, each integration test took 493 microseconds to run. As shown in the integration tests, the algorithm is able to consider the heading of the plane and balance minimal plane turning and path length. Each image that we receive is sent back from the plane and cropped into a set of overlapping sub-images. These sub-images are sent through a small convolutional layer to determine if the sub-image contains a target. This pre-processing step is necessary to cut down on the number of images getting sent into the more complex convolutional layer and to shorten the overall classification time. If a sub-image is determined to contain a target, it will be passed through the tiny YOLO v3 object detection model for classification. The initial classifier model was trained on 80,000 synthetic targets on real background images taken with our camera. The object detection model was then trained on 13,000 synthetic images from each alphanumeric and shape. At test flights, this model has a 70% accuracy for shape classification, a 30% accuracy for alphanumeric classification, and a 20% accuracy for the classification of both colors present on the target. At the competition, 2 image recognition team members will be doing real-time manual image recognition in order to identify any targets that the classification software may have missed. The images will be sent to an imagery operator through a React frontend, which allows the user to select and classify targets by dragging boxes over the target and entering its characteristics in the right sidebar. The characteristics of all unique targets will be passed to the interoperability system through the submission pipeline. The Unmanned Ground Vehicle, or UGV, has completed a multitude of tests, from static and dynamic loading tests to drop and drive testing. The UGV can sustain constant 2G loads at maximum weight. This requirement was determined based on acceleration data acquired during several parachute-assisted drop tests. In addition to the tests to acquire acceleration data, the UGV has been thrown at least 10 times from a 45-foot building, successfully landing safely near the target area 90% of the time. Following drop tests, Drive tests show that the UGV can drive with relatively accurate waypoint navigation. A total of 3 full mission tests were conducted with Phoenix 3. All tests were conducted at a local RC airfield that resembles similar conditions to Webster Field of the Maryland competition site. These tests were held in varying weather conditions to ensure that the UAS is capable of successful performance in different environmental conditions. The full mission tests revealed flaws in image recognition system and the team's newly developed obstacle avoidance scheme. This data was used to refine the algorithms. They also revealed that the communication between the UAV and the ground station was subnominal. The team used this data to upgrade the communication hardware with RFD 900 plus ultra long-range radio modem and develop a tracking ground station antenna system. The scores of the 3 full mission tests were 70.5, 77, and 75% respectively. The average score was 74.2%. UAV Austin anticipates to receive approximately 79% at the competition given the extra time.